Good morning. Welcome to Chapter 7, Type System. In Chapter 6, we introduce the control flow. And in this chapter, Chapter 7 and Chapter 8, we are going to talk about the data type and data structure. Data type. In the programming language, we have primitive and non-primitive data type. And usually, the data type we talk about is the primitive one. You have float, you have double, that's for real number. You have integer, byte, short, int, long, that's for integer. This is actually using Java as an example. We have Boolean type, we have character type, and then we have the reference type called non-primitive. And some language has the pointer, and some language have the structure or object, or the enum type, enumeration type. So these are different types for the programming languages. And on the right-hand side, we have the raw data type. We have the data for qualitative data, quantity data. So basically, the real data is just like the right-hand side, and then we actually need to use the data type unwrapped by the programming language to support it. So we may have the qualitative data or quantitative data, and we try to make chart, pie chart or the bar chart for it. And the data also may have the discrete data or continuous data. So these are the real world data type. And then on the left hand side, we have a programming languages data type that support the right hand side data. So data type, we have developed an intuitive notion of what type are, and what's behind the intuition is basically a collection of value from a domain. And what we say about domain usually in programming language is the integer, the natural number, the real number. That's the domain we talk about. And that's actually for primitive data type. And then you have the internal structure for bunch of data. That actually usually is the structure or your records or object. That's the data structure, internal structure. And a collection of well-defined operation, not just like a push pop for the step. So there are primitive data type, reference data type, and also maybe abstract data type. And the abstract data type also named a short form of ADT. Here in this chapter, we discuss these different kind of data type and also the operation associated with it, and then in terms of mechanism to check it, what things need to be done in the programming language and the compiler to support it. So the purpose of data type is associated with a set of operations. Type provide implicit context for many operations. In OOP environment, they are called the methods. So the operation are called as method, and sometimes we use the function to support it. And semantic validity, type limits the set of operations that may be performed in a semantically valid program. They prevent the programmer from adding a character and a record or from taking the arctangents of a set. And then higher readability, the type are specified explicitly in the source program. Well, this actually is no longer that essential because recent programming languages go for the type inference, for example, like JavaScript, and recent Java 10 add this type inference into the feature. So whether having the type implicitly specified or not, it is questionable. It is whether it's a good thing or not is questionable. But some language like Python, starting from 3.5, it support a type hint. Python used to have no type when you actually write a program. You don't need to declare the type for a variable, but actually for parameter and return type, sometimes it's actually not as convenient, so they start to use the hint. So this part, readability, whether having type is good or bad, that can be a debatable issue. Performance optimization, if types are known at compile time, they can be used to drive important performance optimization. This is actually talking about the type for register. If you really can put all the data into the register of certain type, that can be optimized. And also that actually will help the compiler to decide the proper processing unit, such as a floating point processing unit or integer processing unit, or some extra vector processing unit. So it actually will help the performance boost up if you really know the type properly at compile time. Data type. What are the type good for? Implicit content, check-in, and then it catch enough of them to be useful. And also polymorphism result when the compiler find that it doesn't need to know certain things, and this actually is good for having data type. Type system. A type system contains of the following two things: a mechanism to define type. So type system including a mechanism to define type. Second, a set of rules for type equivalence, type compatibility, and type inference. So there are three things in type system for the rule: the equivalence, the compatibility, and then the inference. These constructs include names, constants, variable and record fields, parameter, subroutines, and the literal constants and expressions. Type system, type equivalence, type compatibility, type inference. Type equivalence rule determine when the type of two values are the same or not. Actually, that is for type equivalence. Type compatibility rule determine a value of a given type can be used in a given context. So this usually is related to polymorphism or casting, those type of things. Type inference is usually for some, you determine the return type or some type based on the input type or some surrounding context. In a language with polymorphic variable parameters, it may be important to distinguish between the type of reference or pointer and the type of the object to which it refers. And a given name may refer to objects of different type at different times. So type can be swapped or changed for some language that provide a polymorphic variable. So there is a strong type or weak type issue. So data type, we have strong type that have become popular buzzwords like structured programming. Informally, it means that a language prevents you from applying an operation to data on which it is not appropriate. This is strong type. And static typing means that strongly typed and that the compiler can do all the checking at compile time. That's static type. So on the other side, we compared to the strong type, we have weak typing. And for static typing, we have the dynamic typing. So whether strong type is good or bad, dynamic typing is good or bad, it actually depends on the application. So dynamic typing determines the data type at the runtime, and we call it type inference. That's because the growing popularity of scripting language that had that number of prominent software developers to publicly question the value of static typing. Excuse me. They ask, given that we can't check everything at compile time, how much pain it is to work? Is it worth to check since we can? Since we cannot check everything at compile time, then why don't we check it at runtime? As a general rule, it is easier to write type correct code than to prove that we have done so. And static typing requires some such proof. The complexity of static typing increases correspondingly. Anyone who has written intensively in Ada or C++ on the one hand, and in Python and Scheme on the other. So Python Scheme support more dynamic typing, and Ada C++ show more static typing, and cannot help but stuck at how much easier it is to write code. So either side has supporters. Dynamic typing determines data type at runtime. Dynamic checking incurs some runtime overhead, so they are overhead, and usually it's done by scripting language and may delay the discovery of bugs. But this is increasingly seen as insignificant in comparison to the potential increase in human productivity. There are ways to hide those overhead, and the hardware are improving, networking are improving, so the overhead over the time start to be not as important as before. The choice between static and dynamic typing promises to provide one of the most interesting language debates of the coming decades. So for the time being, the trend is toward supporting both dynamic and static typing, but some languages, especially scripting languages, like to have dynamic checking. So here is a 4-quadrant. We use a strong typing, weak typing, static typing, and the dynamic typing. We create 4-quadrant. For C++, weak typing, but actually static typing. Why these are weak typing? That's because something like pointer, you can treat it as integer, you can assign it with proper casting or even no casting, you can convert data to different type, and you have byte, short, different data type can be converted to integer. There are a lot of things that C++ are flexible. And some languages like Java, Scala, or C# are very strong type. You have to declare them then and stick to it. But recently, Java picked up some of the type inference, make it as no longer a strong type. But it is a trend that we still need to watch. And some languages are strong type, but very dynamic typing like Erlang Coercion or Python. Some languages are weak type, but also dynamic, like Perl, Visual Basic, PHP or JavaScript. And these actually, on the left-hand side, the dynamic typing mostly are scripting language. On the right-hand side, the more functional language will have more stronger type and then more static type. Type system. Common Lisp is a strong type language, but not statically typed. Ada is static typed. Pascal is almost static typed. Java is static typed with non-trivial mix of things that can be checked statically and the things that have to check dynamically, because Java supports polymorphic methods. C has become more strong typed with each new version, but loopholes still remain. I don't think that the loopholes of C language can be totally taken away, because as a high-level language close to machine code, C won't be as strong type as other more conceptual or functional languages. Overview of the chapter on data type. We basically talk about the meaning of types, polymorphism, orthogonality, type, and then rechecking the equivalence, compatibility, inference. And then we talk about the generic and composite data type or compound type. This composite type or compound type belong to chapter 8. And in the third edition of the textbook, actually, chapter 7 and 8 are combined. So basically, we look at these data type for chapter 7 and 8 as one chapter. And we will have this week 5 dedicated to chapter 7 and 8 for data type. Generic programming. What is generic programming? First, let's understand what's object programming. Object-oriented programming is based on 3 concepts: encapsulation, inheritance, polymorphism. So basically, you have the encapsulation, so the data actually is abstract. So you can only use some method to access it. And then you have inheritance, so some data can be shared and put into a abstract class or upper class to handle it. And polymorphism, you allow some of the type checking at runtime, and some of the operation can be polymorphic. That's the object-oriented programming. And then later, because the polymorphism, the OOP is no longer enough. So the idea of the generic programming or programming with templates is to define the family of function or class is invented. And then we have the functional programming that is actually also very abstract, that actually not only the control flow have been changed to functional programming, but also the data are also being different. So functional programming is when function and not object or procedure are used as the fundamental building block of a program. So we have the following different topic: first class functions, higher order function, lexical closure, pattern matching, single assignment, lazy evaluation, garbage collection, type inference, tail code optimization, list of comprehension, and monadic effect. So functional programming right now still a new topic, even though functional programming have been there for quite many decades since this program language is out. But now it still attracts a lot of attention for as a programming feature. And recently, people move more to generic programming, and Java language is also a supporter for generic programming. Same thing for C++. So basic C, we had a procedural and structural programming, and C++ started support object-oriented programming, and later version of C++ support a template for generic programming, and C++ 11 start to pick up the closure of the function and more newer feature to support the function programming. So functional programming and vanilla machine imperative programming language. The vanilla machine is command state, and you operate on them sequentially or structurally. And right hand side, we have functional programming. You have input, function, and output. Lambda calculus. These two are different programming paradigm. Which language is more functional? Groovy, Kotlin, Scala, or Java? And these actually, there are some debates. And right now, actually, Kotlin, because it's supported by Google, Oracle, so it become a popular language on top of Java virtual machine. And Java 9 just out, and recently Java 10 is out. But these are just a half a year version. We are waiting for Java 11. That will be a 3-year edition. We will look at Java. So next, Java virtual machine language. People still waiting for it, for successful. For the time being, Scala is taking majority of the market, but as I say, Kotlin is catching up because of strong support from Google. Lecture 2, type system. Type system, denotational, structural, and abstraction-based view. Here are different types. We have character, byte, show, integer, long, float, double, void, and boolean. As you can see, this one is pretty much what is supported by Java. So the primitive data type, you have unsigned integer of 16-bit for Java, that's character type. And you have 8-bit byte, you have 16-bit short, and then integer, non-integer, and float, double, and boolean, and there's also another type called void type. And something you need to know about Java is this different data type is supported cross-platform, so it actually is platform independent. So no matter what machine you run on, the data type is the same. And then the function that's supported is the same. And it actually depends on the Java virtual machine to provide a service for these different classes. And Java virtual machine will be designed in different flavor on different platform, but it hides those incompatibility of hardware from the programmer. So these are the domain. Type system common term. We have discrete type, we have scalar type. What actually scalar is one-dimensional. You have the discrete type, or you have real type for the scalar. And then we have the discrete type for countable type as integer type. You have integer, boolean, character, enumeration, and sum range. So the upper part actually is countable. It is discrete, so you have the 1, 2, 3, whatever. And this scalar type is actually a discrete number like this 1, 2, 3, or it can be 3.5, but only one data. We call it scalar. And enumeration type in Pascal, you can define a type called weekday, and then you have Sunday, Monday, Tuesday, Wednesday, Thursday, something like that. And you can assign successor of the day will be assigned to tomorrow, and successor actually is a function. So, but equivalently, you will have someday 0, 1, 2, 3, 4, 5, 6, or you study from 1 if in Pascal. Okay, that's emulation type. And in C language, you can use the define, or you can use C's enum type or C plus enum type. And C11 has new supported type called enum. It's actually also counting integer. But to me, there are several different languages support that, and I believe personally, I think integer type is good enough. The enum type, you have extra overhead to program it, even though the variable is more readable, but actually, usually you can just put some comment to comment that. And emu type, actually, to me, it doesn't buy me better performance, and actually will require more overhead when we do programming. So I personally do not strongly recommend the enum type, but enum type usually also is not a topic to be taught in the introductory programming language, but I don't know why this data type is still there just to make the compiler bigger. There are some application, but because the enum type actually is a sub-range type for integer, so it makes it not as practical. Sub-range. So we have original list of these, and you can use the range of 0 to 4, index range of 5 to 9, you get different data. And you can use sub-range in Pascal 0.100, that will be from 0 to 100. And Ada also had a sub-range type for list. You can do this for sub-range of a list as a Python code. And -5 to the end, this is -1, 2, 3, 4, 5, so this is -5. We studied from -5 to the end of the list. So there are certain range rule, start, and step for the range function in Python, and you can take some parameter out, just leave the first one or leave the second one. They will have different definition. Type, pointer, ages, and reference. We have a ages or a pointer that holding the ages that will pointing to a object. So for a function that right hand side, we have integer equals 3. So we may have a storage ages 2001, and we actually put the value 3 in the A. And then we may have a pointer that's a star type. Actually, it hold the data for A, and it points to A. And then we have another pointer that's holding the ages of that pointer. So it actually stores 4001 for the ages of this pointer. So this one's data A for 3. Its age is 2001. We have a pointer that's holding the ages for the 2001, and the pointer has the ages of 4001. And then there's a pointer to the pointer that is value of 4001, and it has the ages of 6001. So this ampersand sign I call it ages of. So this it assign the ages of A to the pointer PTR, and PTR's body is an integer. PPTR's body, that's the second degree pointer, is an integer. So I usually call the ampersand sign as the edges of, so edges of A assigned to pointer, then pointer holding an edges. And then edges of pointer sent to the pointer of pointer, PPTR. And the star sign usually call it content. So when I declare the content of a pointer is an integer, so pointer PTR is a pointer to an integer. Type pointer to function. In addition to using the pointer for data type, you can also use a pointer as a pointer to a function. So here I declare a fptr as the functional pointer to a function of two input integer type. And then this fptr's body is integer function. So fptr is a function to an pointing to a function of integer in the integer argument type. So I can assign function A to fptr, and then I run function A for 3 and 4. And I can also assign function B to fptr, and then we run the function B for 5 and 6. And then we execute different function by assigning different function pointer for the function. So right here we have XML built-in data type. As you can see, it actually is quite complicated. I just want to show this chart to make sure that you know that some scripting language or markup language, the data type can be very complicated and very decorated, so you actually can apply them to different data variables. Type system, composite data type. In the previous lectures part, we talked more about the primitive data type or single data type. And then we talking about a pointer for it. Now we are talking about a composite data type. Composite data type, we have record, variant, records, array, set, dictionary, pointer. Pointer is the left-hand side value, L value. Or it can be a reference type. And reference type, as we mentioned before, reference type is a pointer type with limitation. And these topics are in chapter A. We have list type and a file type. So structure, we have a structure of employee that has X and Y. And actually these two are a structure of different data type. And totally for this structure, we have 5 bytes. And for union is different from structure. Union are data fields that share the same data field. So for this one, union employee type has a type variable E, and then these two are sharing the same space. So basically, these two will totally have 4 bytes since the flow is longer. And compared to the left-hand side have 5 bytes. So these two you have to compare. And usually structure is easier to use. And pointer and reference. Pointer and reference are different. And we have the stack, and there might be a pointer to reference type in the heap. So pointer is the memory address of a variable. The reference is an alias of different name. So reference is a name, pointer is an address. So that's the fundamental difference. The pointer variable returns the value at the address location stored in the pointer variable, which is preceded with the sign star. We call it the reference. So actually that is the body of the pointer. And then the reference variable return the address of a variable preceded by the reference variable with sign x sign. That's an alias. The pointer variable can refer to null variable, and the reference variable can never be referred to null. But this is not true for Java. Because Java's reference is somewhat having the feature for pointers. So this table is more true for C, C++. Type 2 polymorphism and orthogonality. We talk about orthogonality and polymorphism. Polymorphism takes its name from the Greek, meaning having multiple forms. It applies to the core, both data structure and subroutine. And in fact, there are 4 types of polymorphism. There are ad hoc polymorphism and the universal polymorphism. Ad hoc is when you just use it, you determine to provide polymorphism, so they are casting or coercion polymorphism, and another type is overloading, overriding polymorphism. Those are ad hoc polymorphism. The other 2 types are inclusion polymorphism, or called subtype polymorphism. And another one is the parametric or generic polymorphism. These are the 2 main new trends for the polymorphism. So in parametric polymorphism part, the code takes type as parameter, just call generic. Subtype polymorphism, the code is designed to work with the value of some specific type T, but programmer can define additional type to be the extensions or refinement of T. Generic. Right here we have a generic class. So we declare a reactive buffer of the item type. And actually this item type can be replaced by any data type. So that's a buffer of container that has a generic data type. We can call it generic container. And for this generic container, we can have add to buffer, remove from buffer, both supporting any generic item. The next one is generic sys implementation for generic swap. Okay, a swap function is usually very useful, but some language doesn't have generic data type. You will have to rewrite the same function several times. And right here, we support a generic data type. The generic variable we use is using void instead of using object. That's the way we use a pointer in generic way. Subtype polymorphism, where C++, LFL, OCaml, Java, and C#. And here we have the polymorphism for Java. So here we have a vector, and then we assign new vector to it. And then the vector originally has put a element of 5 in there, and then later we put a string in there. But since this is a vector, and we want to allow both of them to work, so actually we need to have a function of return to that actually accept the object type. Both of them can accept either number or string. Dynamic typing language with support for unified polymorphism, and including for Python, including the following: dynamic typing, inheritance, multiple inheritance, overloading, overriding, polymorphism, and dynamic binding. Type system, orthogonality. Orthogonality is useful goal in the design for a language, particularly in its type system. A collection of features is orthogonal if there's no restriction on the way in which feature can be combined. So if we had some feature together, the program is called or language is called orthogonal. If any combination that's legal can be done to vector or any other data type, we call the data type as orthogonal. So one example, Pascal is more orthogonal than Fortran, but it does not permit variant record as arbitrary field of other records. So let's break the orthogonality. C and alpha 68. No distinction between statement and expression. Orthogonality is nice primarily because it makes the language more readable, more easy to understand, and easy to use and easy to reason about. So for orthogonality, C language we can cast to void type. So basically, we actually assign the result for insert in table, symbol table, function, and the return type for full underline index. And we actually, if we don't care where you win, we can convert it back to a void type. So the data is returned, but it's converted to void type. And casting is optional. Imply is omitted. Pascal has the type inference using the VAR, the dummy data type. He used a dummy type. Orthogonality erase the value of variables. For pointer type, assign the value null. For Java, the corresponding object will be clean if you assign null to a reference data type. That actually is a mark that the object will be lost, and then the object is probably recollected, but a reference variable may still be existing. For enumeration, we can add extra one of the above alternative to the set of possible values. That actually is a extra type to handle the to make sure it can allow value of optional value to provide orthogonality. But these two techniques are very difficult. They don't generally generalize to type that already make use of all available bit patterns in the underlying implementation. For functional language, it provides special type constructor called option or maybe. That actually is some sort of way of getting rid of such problem. Orthogonality, OCaml. Here is an OCaml statement. Let divide n and numerator and denominator, and the return type is 14-point type. So if d match 0, we return nothing. So the option actually provide you two options. Either you actually put underline means nothing else. So you actually, if you see a 0, you provide a none. Otherwise, you provide some function that actually has that x integer division by d. So that's a division. And showing v string, matching v as a string. And if there's none, we actually print question mark. That's when we have the division by 0. We will do that, and the sum function will perform the string of float. So this will help you to print out the division. So sweep language, we have division like this, and then return double type. If d equals 0, we return nil. That's another option variable. Or otherwise, we return n divided by d. So the function show function similar to the optimal case. And here is called the aggregate. So the aggregate assigned into P and A are positional. The aggregate assigned Q to and B name their element implicitly. So here the eta aggregate initialization, we have a record and we try to initiate it. So a person is a record, and we also have basically have variable called P and Q that of person type. A and B are array of integers. So we assign for P. Actually, this P we have name and string. So the name is Jiang Dou 37, and that's positional. We don't actually by the out of order assignment, and then second one is using our order assignment. So we have age assigned with 36, name we assign with Jiang Dou, and such out of order assignment is also allowed in Python. So A we actually is a positional assignment. We assign 103030300 by the position, and B we provide out of the assignment, or this one 357 being assigned, all being assigned by 3, and 1 we assign by 1, and all others like 246A 9 we all assign with 0. Now we'll provide the same result like A. Excuse me. Type equivalence. In the following 3 lectures, we will talk about the type checking. So we have type checking, type equivalence, type compatibility, and type inference in this chapter 7. So this is the first one, type equivalence. Type equivalence, type system has 3 rules. We have type equivalence, type compatibility, and type inference. And type equivalence is very strict. You need to have a type to check in for equality. Compatible as is compatible is okay. So type equivalence is closer, need to be almost like overlap. Type compatible as you have the compatibility, it's okay. Type inference is to determine some of the type. So type checking, compatibility is the more useful concept, but it tells you what you could do, you can do. In turn, the terms are often used interchangeably. So actually, type compatibility and type equivalence sometimes are mixed. But actually, type equivalence is a little bit more strict, and type compatibility is more relaxed, but sometimes they are used interchangeably. Type equivalence, certain format does not matter. So how we define it, actually, whether in this way or this way is the same, or even this way is the same. We just declare 2 integer type. So these 3, we call it type equivalent. When we declare the type, they are the same. Because usually we don't really care about the program style. We only care about the positional declaration, and even variable name is sometimes not as important. The major approach, structural equivalence and name equivalence. So There are two ways. So here, if I use the structural equivalence, some structure integer C and D will be equivalent to this. That's if you use the structural equivalent. If you need to use the name equivalence, then no, this one doesn't support the name equivalence. So structural equivalence is based on some notion of meaning behind those declarations, but can equate type programmer doesn't intend to. Consider more low level. Name equivalent more fashionable these days because we wanted the declarants to be the same. Then we can check the type implicitly without guessing just integer flow. Then you need to go down to low level to check. Especially when we do some internet transmission of data type like JSON or something, we like to know about the name in advance so we can take the data from the internet. Instead of making it compatible in low level but not readable for a programmer or data processor. The difference between all these approaches boils down to where you draw the line between the important and unimportant difference of the type description. So it's actually really on how much you care about the type. In all three schemes described in the book, we begin with putting every type of description in the standard form that take care of obvious unimportant distinction like these above. So name equivalence. Here we have the name equivalence. You can provide alias for type. So type new type equals old type. That's a type alias. And then define type that's used for C language. Old days with new days. That's C language. And type new type equals old type. That's for OGO 68, OGO 60. Semantically equivalent alias type. We assign type integer 16 underline T with mode type T. Actually used for sometimes for the register setting for low level programming. Mode T, we have my permission equals S I user, S I W user, S I R group. That's the permission word. And that's a 16-bit data. If my permission word and the setting of the IW USR, so that actually this one is a constant for you to set or unset some bit level bit flags. So the 16-bit unsigned integer and the mode type are actually equivalent alias type. And they are semantically distinct alias type. So Celsius temperature, that's real. Fahrenheit, that's also real. But we actually have two different types for Celsius integer or Fahrenheit. But actually, both of these two can use the real data type to replace them. So creating or using this new data type actually, to me, is an overhead. As a programmer, I actually don't like to define some type like this as a separate type, and then later you have a lot of type checking problem. Although some languages do support such name equivalence checking, like Ada, but to me Ada actually is too much overhead. type checking. Structural equivalence depends on simple comparison of type description, substitute out all names. So it spans all the way to built-in type. So for type checking, actually you would have more like a structure, and then you need to actually expand all of the structural information and then go down to comparison of each built-in type. So basically, you need to know about the memory layout for each structure so that you can do fair comparison between two different types. So original type are equivalent if the expanded type description are the same. So type conversion and cuts. And here are the Java's casting rule. So number one, same type for left-hand side and right-hand side for the assignment. Second, automatic conversion of the right-hand side to the left-hand side as implicit casting. So you may have the automatic conversion. That's a parameter matching, but allow the conversion for the type, especially from integer to double, that usually is taken. So implicit casting for Java, you can see the right-hand side map. Character can be casted to integer, and integer can be casted to long. And then byte and short can be casted to integer, and then integer can be casted to float and double without explicitly declaring them. And Java also support auto-boxing, auto-unboxing to convert from a simple primitive data type byte to its wrapper byte, a capital B byte object type. This is called auto-boxing and auto-unboxing. Type conversion to ADA. We have n as integer, we have r as real, we have t as test score, we have c as Celsius t, and later we actually have a t as test score and n as runtime semantic check require. A t is the type called test score type. That's actually integer type. And n is an integer of t type. That actually is checking whether there's no checking needed. Every test score is an integer. So t equals testing score of n. That's runtime checking. And r equals real of n. So that actually n is actually an integer. So you need to convert it to real number. That's a runtime conversion. R from a real type number converted back to integer. That's also need a runtime conversion and checking. C is a Celsius temperature. You convert it to integer. It's already a integer type. So no need for that. And then n is a integer that will convert it to Celsius temperature type. No integer, because n and Celsius temperature are both integers, so runtime code needed. Non-converting typecasting is called type one. Conversion that does not change bit, n bit or to n bit conversion. That's non-converting typecasting. Usually, what is type converting casting? For example, if my number of bits are not equivalent, I convert from an integer to long or long back to integer. I need to take care of the conversion, especially the boundary condition. That actually I need to do some work that will be a converting type casting. But what is a non-converting type casting? That actually is some conversion, I just do bit level conversion, and I really don't care about how to interpret it and then convert it with some type conversion. So occasionally in system program, one need to change the type of value without changing the underlying implementation. One common example occurs in memory allocation of algorithm, which a large value array of bytes to representative. Then reinterpreted, actually here, be careful, it's reinterpreted. It's a way people interpret the concept of array as pointer or integer, and pointer or integer or user allocated data structure, they actually are more than 8-bit the type format. So actually you need to do conversion to do different interpretation. But the non-converting type casting actually is, I just give you the bit. I don't really know about how you interpret it, but I support it. That's non-converting type casting. Type compatibility. Most languages do not require equivalence of two types in exact every context. Actually, they allow some casting, allow some implicit casting, and those languages actually will not require the 100% equivalence. Instead, they merely say that value types are compatible with the content it appears. In an assignment statement, the type of the right-hand side must be compatible with that of the left-hand side, as long as the right side be converted to the proper coercion to the type of the left-hand side or proper type that left-hand side can accept. So that can be done implicitly or explicitly. Same thing for parameter or operand matching. That's actually another assignment to be done. And there's a type compatibility issue. If you provide some variable of mismatch type, it will be raising some exception. Type coercion. Whether a language allows a value of one type to be used in a context that expects another, the language implementation must perform an automatic implicit conversion to the expected type. That's type coercion. So the language allows value to be changed from one type to another, and we call this coercion. And usually coercion implies the external explicit casting. But some implementation do have the implicit conversion done automatically. So here is the C-type casting. And as you can see, the right-hand side is the C-type casting that you actually don't need the explicit casting. You can just assign a value and C compiler will adjust for you. That's implicit conversion. So there might be explicit conversion, implicit casting, or explicit conversion, explicit casting, or sometimes it's a mixed mode, can have different operand casting of different type. And coercion is implicit conversion. Disadvantage: decrease the type error detection capability of the compiler if we use the implicit casting. In most languages, widening conversion of numeric type expression can be coerced. In data, there are virtually no coercion in expression. Actually, also related to the data type design for the language. Type checking coercion. When an expression of one type is used in the context where different type is expected, one normally gets the type error. But what about this? Many languages allow things like this and coerce an expression to be the proper type. Coercion can be based just on the type of operand or take into account expected type from the surrounding text as well. Fortran has a lot of coercion, all based on operand type. So type checking coercion is conversion to different type. Many languages allow this thing, so coercion expression to a proper type is fine. Coercion can be done just the type of operand and can take into account the expected type of the surrounding context. So coercion actually sometimes like in Java, when you put out something, coercion will be used. So that actually is done for the surrounding context to convert the integer or double into a string. Type checking. C has lots of coercion too, but they have simpler rule. All floating point expression become double in the C language assignments. All show integer character will be converted to integer in the expression. So basically in C, C++, or even Java, use the double and integer type are safer because you don't need to have any type of conversion. Unless that your integer is super long, then you use the long variable. Ada allow little conversion. Pascal and Fortran have little more rules. C++ go hardwire with coercion, so they basically allow a lot of different coercion. Coercion in C. In C language, it allows value of the most numerical type to be intermixed with expression in expression and will coerce type back and forth if necessary. So here we have a show integer s, long integer unsigned L, and C, F, D. So we try to assign those values to different variables. So for first one, we convert a unsigned long integer L to S. So lower order bits are interpreted as a signed variable. So we have 64-bit. We assign to a 16-bit show integer. We just take the 16-bit, that's only 1/4 of the long integer, into the S variable. May lose some bits, but that's the way we convert it. Also, we can use S to assign to L, but since S is a show integer that has sign, so we need to do sign extension to make it compatible. And for C to assign to S, both of them are 16-bit. So they are fine. We assign L to F. L is a long integer. F is a floating point. That's only 32-bit. So data conversion is involved to do the conversion. Same thing from F to D. That's a 32-bit floating point to 64-bit floating point. There are certain algorithms need to be done to make that conversion. Same thing D to F. So technique used in coercion of a C language, we have sign extension. To keep it positive, we have 0 extension. To keep it negative, we have 1 extension. That's called sign extension. And over here, we have long type to convert it to short type. And on the right-hand side, we have long to double to float to double to compare the 3 different data types and the rules of precision. If we assign a data of the longer format to a shorter format, that may cause the loss of precision. So coercion in Ada. Here we have the D as a weekday converted to K. K is a workday. And then there's a runtime checking to be done. D has more value, K has less value. So that need to have the runtime checking. And K back to D, there's no checking needed. D to C, C is a calendar column. It's not a workday or integer, so there's a static semantic error. And the two data types are not actually compatible. Overloading and coercion. Overloading and coercion are two the so-called ad hoc polymorphism. We have noted that the overload and the coercion can sometimes be used to achieve the same similar effect. Coercion could still allow plus sign to take integer argument, but they would always be converted to real. In some languages like Java, if one of the operand is string type or character type, the number will be converted to string due to the overloading of the plus sign. Plus sign is overloaded with multiple plus addition or appending for the string. So right here we have a string concatenation for the sum of plus sign A plus and D plus B plus is and plus sum. And the lower part is the process of combining the whole thing back to a message. Universal container type. Polymorphism, as we say, has the ad hoc polymorphism, and we also support the universal variable type if you use a void. But remember that void actually also will lose some property from your object, so you sometimes need to convert it back to the original format. So void pointer can be a pointer to any type, but it can only be used after it's committed to a certain real address. Java container of object. When an object is removed from a container, it must be assigned into a variable of an appropriate class before. So the example on the right-hand side, we have created a stack, and then we create a string hi mom, and then full f equal new full, and then my stack will push s that is actually a string into there. I also push a f, that f actually is a full type, so that stack, my stack is of the generic data type. It's sometimes you need to check whether the library code or the class you use stack whether supporting it or not. So in a language without type tag, the assignment of universal reference into an object or specific reference type cannot be checked because the objects are not self-descriptive. In that case, we need to use the context for type inference. There's no way to identify their type at runtime. The program must therefore resort to a unchecked type conversion. Lecture 6, Type Inference. Type inference. What is type inference? Let's look at one example. So right here we have type propagation. Let's look at this type propagation. And this example will explain well for type inference. So basically we have a function of full function. We have a function of bar function. We have a class. That's a bar, that's an object of goodbye and hello. That's one variable. But now I have a full function. I have a full function and I have a bar function. So this bar function, I put in this goodbye as string type and hello both are string type. And then into the function I call bar, and then bar put in the function for function call for bar. And then these two A and B swap. B go to A go to, so this one A and B swap to go to call the full function. So basically my hello go to B and B go to X. Sorry, I make a mistake. So basically my hello go to B and B go to X. B go to X, and then goodbye go to A and goodbye go to Y. Goodbye go to A and go to Y. So here Y is actually goodbye. And then X is actually the hello. And then here we have a plus sign. And so this plus sign actually have to depend on the data type over there. And apparently this is not really an addition, but it's actually a concatenation. So we call this a type propagation and then type inference. And then right here we need to use the concatenation to operate. And then we become goodbye, hello, and then goodbye. So we got a hello and goodbye to here, all the way return to class. So eventually this class will get hello and concatenated it with goodbye. So that's the type inference based using the type propagation. We have data, we propagate into the functional call, and it propagates the type, and then determine the operator in this function. So this had to be the type had to be done dynamically in order to perform this type inference by type propagation. So this is one type of type inference. We call it type propagation. You can see the function type as orange bars containing the reference to abstract value. Function declaration will cause such type to be created and added to the variable that names the function. The purple box are propagation strategy. There are two calls in the program corresponding to the two purple call boxes. At the top is a simple box that handles the plus operator, and that actually is concatenation. And if full function receive two numbers, then that plus will become a plus sign, will be an addition. So that's a type propagation for type inference. Let's go back to the initial part for type inference. So what determines the type of overall expression? The result of a arithmetic operator had the same type as the operand. So the right-hand side value determines the left-hand side value if there is no explicit casting or definition. The result of a comparison is usually a Boolean. The result of a function call has the type declared in the function's header. The result of a assignment has the same type as the left-hand side. In a few classes, however, the answer is not obvious. In particular, operations that subrange or composite objects do not necessarily preserve the type. So sometimes this type inference is not really that easy to be performed. So type inference permit modern language, and especially scripting language. The type of variable is inferred to be integer from the declaration statement. So basically, we have declaration for this integer variable arguments, and then when we actually use the function, we put a variable that had to be a variable integer type, and then we can return argument 1, argument 2 by addition. The type inference function, which automatically specifies the type that can perform inference, if the necessary minimum type is specified like the figure, this function is used. The advantage where error can be checked at the early stage can be realized without specifying the type of all variable and function. So that's using type inference to avoid the early declaration of all types. Declare type in C++. In C++, we have this declare type. In the C language, we have type define. And these are two different things. And we can use declare type of A plus B for sum. So actually, there's a type name for this, and A type, T type, maybe passing in an integer. We based on that declare type, the sum is determined by the type of A and B. Type checking in ML languages. Type checking in ML language. Most sophisticated type of form of type inference occur in ML family because these family language are functional language, and functional languages tend to have no type declaration. Programmer has the option of declaring the type of object in this language. Okay, you can do that, but in which case the compiler behave much like that of a statically typed language. So that actually will be more or less like imperative language type declaration. And programmer may choose not to specify the type, and that's actually what preferred by functional programming. The compiler has to infer them. So type checking for ML language, the key inference mechanism to unify the type information available for two expressions whenever the rule of the type system say that the type must be the same. So this one actually is trying to unify the information for the two expressions. So that means that try to use a closer type to unify the whole two expressions. And any discovery inconsistent or identify a static semantic error, there may be different data type, but at the end, those data types have to be compatible. Otherwise, you cannot unify them. Any expression whose type remains incomplete specified after inference is automatic polymorphic. This is the implicit parametric polymorphism. So there's a way to provide this parametric polymorphism. ML language, ML typing static, strong, and inferred. Type check at compile time. type mixing will be done implicitly. So functional language, static, strong, and then inferred. And that, as we see before, it actually is in the quadrant 1, strong and static. Quadrant 1 as the functional language corner. Even though type inference basic types still exist, ML created by Miner to specifically utilize the Hindley-Milner type inference algorithm to automatically infer type of expression. Type inference. Type inference, the ability of a programming language to automatically detect the data type of a variable. A compiler is often able to infer the type of a variable without explicitly type annotation having been given. Why it is useful? A programmer does not have to explicitly define type annotation while still maintaining about the same level of type safety. Type often cluster program and slow down programmer efficiency. Okay, here has a ML type inference. We have function f of x equal to +1. We have a value integer it equals function integer to integer. So basically, the variable it plus sign has two types. It can be integer to integer or real to real for the assignment. 2 is the integer type. So it implies that 2 and x are integer to integer multiplication. So f of x return that should also be a integer function. So it becomes a integer to integer function as type inference. Right here we have a tail recursive Fibonacci function written in OK mode. The inner dot construct introduces the nested scope. The function Fibonacci helper is netted inside the fib. The body of the outer function fib is the expression of the function fib, the expression fib helper 010. The body of fib helper is in the if then else structure. It evaluates either the N2 of the Fibonacci helper N2 parenthesis N1 plus N2 or I1, depending on whether the third argument to FIB, a Fibonacci number helper or not. The keyword REC indicates that the Fibonacci helper is recursive. So REC means it is recursive. So it's actually running the recursive Fibonacci helper of N1, N2, and I. Tail recursive Fibonacci function. We try to minimize the number of operations when after the recursion call is done, especially not to do anything. We will call that function as tail recursive function. So the parameter I of Fibonacci helper must have the type integer because it is added to 1 at the line 4. The parameter n of Fibonacci has the type of integer because it compares I at the line 3 and Fibonacci helper at the line 5. The type of all three arguments must be integer since it has only one call. So the type of N1 and 2 are integer. The type of I is consistent with the earlier interference, so the type of the argument to the recursive call and line 4 are similarly consistent. Since the Fibonacci helper return N2 at the line 3, the result of the call at the line 5 will be an integer. Since Fibonacci intermediately return the result from its own result, the type of Fibonacci will be integer. So here I just explain the detailed steps of determining the type of the function. So basically, we pass through this 0, 1, and 0, and then we got the n1, n2, and I, and then we determine the I and n equality, and then this things, and then you propagate through there, and eventually you will prove that they are integers. So we initially has this 1 over here is integer type. So I plus with it must be integer type. And then we have the n, because we call it, we have the n being assigned with compared to I, that should be the same type. And then we have this helper to have integer, integer, integer. And we backtrack to that n1, n2 because we pass the variable to there. So the function return should be integer type. So all the Fibonacci, I, n, n1, n2 are all integer type. Other type checking for ML1. Here are several different type checking for ML language. You can check for yourself. Type checking, all occurrence of the same identifier has same type. In and if then else expression, the condition is of the type Boolean type. The then else clause has the same type. Programmer defined function has the following type. A function is called the type of a argument that are passed are the same as the type of the parameters in the function's definition. The types of application is the same as the result in the function's definition. Parametric polymorphism. Parametric polymorphism, we also call it as generic. Implicit parametric polymorphism in ML family language are mutually polymorphic. So it's mutually polymorphic. So that minimum of xy equals the following things. So we actually, in OK model, minimum function can be said to have a type of this, this, and this. In Haskell, we have this, this, this. And then while the implicit parameter minimum are x and y, then we think of A as extra. The implicit parameter is a type parameter. ML language provide implicit parametric polymorphism. So we have generic subroutine, generic module, and generic container. Generic module and generic are particularly valuable for creating containers. And then we have generic function that are needed for generic module. So for example, generic subroutine or method, something like generic sorting, that sorting can be used for different data type or different object type. That's valuable for generic subroutine. And we also have the generic module or generic class. And usually those generic class can be used for as a generic container, such as arrays in Java language. That is one example for generic container. So generic, we have generic function, generic data structure, and generic parameters. Here is an example for generic function. So generic function, basically, we accept a function for different data type. On the left-hand side, we have a overloaded function of minimum. So we have the mean, and that mean function has xy integer and non float, and that actually it has two function implementation. On the right-hand side, we only have one function, but we declare the type t, and that t is generic. So you can actually put in different type into here to operate. So you can actually declare the function intermean is a new mean of the integer type. And this mean, we actually put it into right here for the type. And then the less than is a parameter to be passed in to determine the type. So we can declare 4 different types for string mean, integer mean, real mean, and data mean for different data type. And then with different comparator. And generic container for C++ type, we actually have the class. That class actually is a type variable item that you can put in different class that will replace this item. And the maxima item 100, that is a number that allow for declaration. Declaration means that that's a constant to be used for that container. Parametric polymorphism 2 implementation. So for implementation, we have different way of implementing it. For different mechanism, we have explicit way, we have implicit way. This functional language tend to use the implicit implementation, but imperative language used to have explicit implementation. And the different detail feature, you can check this table. So for checking, take notice of this. This is the only one that check the polymorphism at the runtime. Other than that, mostly the imperative language is mostly in compile time, and also definition or instantiation. And only functional language is more runtime or inferred. Implementation option, separate copy, C ++ Ada. That's a common way of doing it. Actually, you made a copy so that you have different copy. So the template used in C++ is more like a macro. So you actually make copy for the core, make copy for data structure, and that template is only a macro, so you can use that as a template, and in terms of the saving of the storage of the data structure, it actually stored into different memory location. So guarantee all instances of a given generic will share the same code at runtime. That is for Java. So Java has more sharing. Java have the object type. In principle, the object shares some polymorphic method. So that actually give another degree of the polymorphism using the inclusion polymorphism object type, creating specialized implementation of a generic code for data type C#. Generic parameter constraints. In Ada language programmer can specify the operation of a generic type parameter by means of trading with clause. So without the with statement, procedure so will be unable to compare A for ordering. So that compare function provided by the with function is the overloaded operator that will be used for the T data type. Generic parameter constraint. In Java and C#, a clean approach to constraint exploring the ability of OO type to inherit the method from parent type or interface. So that is a we can call it as constraint, but the real term for this is bounded. We call it bounded type. So only any class that actually implement extends this type, any type T. So it will be the tree. This T actually determine any tree equal to the comparable T or anything below. The subclasses will be the type that acceptable for T. This is a bounded generic function. Yes. So T type must be a subclass that extends comparable T. And T can be an interface or object. Generic parameter constraint similar to the previous one for C#. Implicit instantiation for C++, we can pass some variable to set a queue starting with the size of 50 or something. That's called implicit instantiation. Generic in C++, Java, and C#. Several of the key trade-offs in the design of generic can be illustrated by comparison of these three languages. C++ is the most ambitious. That means that they provide the most they provide the most feature for polymorphism. So C++ is more ambitious because they provide the most overloaded feature. Even the operator, you provide more overloading functions. And Java and C# provide a generic purely for the sake of polymorphism. So not outside overloading. Actually, C#, C++, and something like Python. Python also allow a lot of overloading for the functions. And that sometimes is dangerous, sometimes hard to understand. So Java and C#, in terms of providing the generics, are more conservative. Java design are heavily influenced by the desire of backward compatibility. So for Java generic function, please check these two courses online. So thank you and bye now.